In this videotape, we're going to continue our work on related rates problems. A list of the problems to be solved on this videotape is available from the director of the math lab. In addition, I want to remind you that there's an earlier videotape on related rates, and that tape and a list of those problems are also available in the math lab. The first problem that we're going to work on today is the following. Assume that oil spilled from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate of 2 feet per second. How fast is the area of the spill increasing when the diameter of the spill is 40 feet? Okay, we have to analyze what information is given in the problem and what we're looking for. So let's make a list of what is given and what we want to find. We are told that the oil spill, okay, it's spreading in a circular pattern whose radius increases at a constant rate of 2 feet per second. So the rate of change of the radius, okay, with respect to time, is 2 feet per second. That is, the radius dt, or dr dt, is plus 2 feet per second, because the radius is increasing. If the radius were decreasing, we'd have a minus in front. But since the radius is increasing, dr dt is plus 2 feet per second. Now we're looking to find how fast is the area of the spill increasing. If A represents the area of the spill, we want to find how fast the area of the spill is increasing, how fast A is increasing when the diameter of the spill is 40 feet. So we want to find the area dt, or dA dt, at the moment when the diameter of the spill is 40 feet. Okay, we have dr dt and we want to find dA dt. The best way to solve a problem like this, if we had an equation linking A and R, we could then differentiate both sides with respect to t and get an equation linking dA dt and dr dt. And since we know dr dt, we'd be able to solve for dA dt. And the key to finding that formula is the fact that it's a circular pattern that the spill is taking. So also under given, we can write the area of a circle is pi r squared. The area of a circle, radius r, is pi r squared. So this is an ideal setup for a related rates problem. We have dr dt, we want dA dt, and we have an equation linking A and R. If we take this equation, A equals pi r squared, and we take derivatives of both sides with respect to t. The derivative of A with respect to A would be 1, but with respect to t, it would be 1 dA dt. The derivative of pi r squared with respect to r would be the constant times the power, r to the 1 less power, or 2 pi r with respect to r. With respect to t, it would be 2 pi r times dr dt. At this stage, we are now ready to substitute in the values that we're given. You do not substitute in too early, because if you were to substitute in, for example, what the radius is at a particular moment, and that would imply that the radius is not changing, okay? And then A would be equal to pi r squared would be a constant. Of course, dA dt would be 0. This is something that is changing. The radius is increasing. However, at this particular moment, we're interested when the diameter of the spill is 40 feet. Well, if the diameter of the spill is 40 feet, then the radius is half the diameter. When the diameter is 40 feet, the radius must be 20 feet. So at the moment when the radius is 20 feet. The diameter is 40, the radius is 20. So let's substitute in. dA dt is equal to 2 pi times r times dr dt. Now r, at this moment, is when the diameter is 40 feet, the radius is 20 feet. And dr dt was in the given, dr dt is plus 2 feet per second. So 2 feet per second. So let's see what we get. We have 20 times 240 times to 80 pi feet times feet per second, or square feet per second. We would expect dA dt to be in terms of an area unit over a time unit, and that's correct here. The unit, we have an area unit over a time unit. So the area is increasing at the rate of 80 pi square feet per second. Now don't let this throw you. Pi is a number, okay? It's approximately 3.14, and therefore this is approximately equal to 251 square feet per second. Okay, so this is a number. It should be treated as such, and you can actually find out that the area at this moment is increasing at the rate of approximately 251 square feet per second. In our second example, a liquid is to be cleared of sediment by pouring it through an inverted cone-shaped filter with height 20 inches and a 5-inch radius at the base. If the liquid is flowing out of the cone at a rate of 4 cubic inches per second, how fast is the depth of the liquid decreasing when the level of the liquid is 12 inches deep? Okay, so we have our inverted cone-shaped filter, and the dimensions of this filter are, there's a 5-inch radius at the base, and the height is 20 inches. Okay, so 5 inches from here to here and 20 inches. Okay, now that's the dimensions of the filter. Okay, there's liquid that's being poured through this filter to clear it of sediment. At any particular moment, there's a certain amount of liquid in the cone. Let's say there's liquid, this is all liquid in the cone. Now, the variables in this problem are R, the radius of the liquid at the liquid level, and H, the depth of the liquid in the cone. And they're changing. In other words, maybe in the beginning of the problem, R was 5 inches and H was 20. But now we have, this is this filter here, and it's dripping out at a rate of 4 cubic inches per second. So R and H are both decreasing. Maybe originally it was up here, and now the level is falling. Imagine an ice cream cone, okay, and there's a little hole in the bottom, and the ice cream is leaking out. Okay, let's see what we're given and what we want to find. We are told that the liquid is flowing out of the cone at the rate of 4 cubic inches per second. Something is 4 cubic inches per second. Now let's say you're not sure which rate of change you're being given. When you see a volume unit over a time unit, that's your tip-off that that's dV dt. However, it should be minus 4 cubic inches per second because the volume is not increasing by that amount. The volume of the material, of the liquid in the cone, is decreasing at that rate. It's dripping out at 4 cubic inches per second. So the rate of change of V with respect to T, dV dt, is minus 4 cubic inches per second because V is decreasing. So we know dV dt, minus 4 cubic inches per second, and we're asked to find how fast is the depth of the liquid decreasing when the level of the liquid is 12 inches deep. The depth of the liquid, the height of the liquid in the filter, is represented by H. So we're looking for dH dt at the moment when the level of the liquid in the filter is 12 inches. So we want to find dH dt, the rate of change of the depth or the height of this liquid, okay, with respect to time, as at the moment when H is 12 inches. So we know dV dt, we want dH dt. An ideal situation would be having an equation that linked V and H. We have a less than perfect situation here because the relevant formula is the formula for the volume of the cone, which is V is 1/3 pi r squared H. This formula will be derived later on this semester in your calculus classes. But for right now, I'm asking you to believe that the volume of a cone is 1/3 pi r squared h, where r is the radius of the cone and h is the height of the cone. Okay, so this problem is a little bit different from the last one because we have dv dt, we want to find dh dt, and instead of the ideal situation, an equation just linking v and h, we have an equation linking v, r, and h. Now what we're looking for is somehow, if we could some way to eliminate r from the problem, then we'd have the perfect setup. An equation just linking v and h, we know dv dt, and we want dh dt. That's the ideal setup. Okay, so let's see if we can figure out how to eliminate r from the problem. In a problem like this, there's usually some auxiliary equation lurking around that we just have to discover, some relationship that would enable us to eliminate r from this problem. Now, can r and h be anything they want to be? For example, is it possible that h would be 20 inches and r would only be 1 inch? That the liquid would choose to stay clustered in the middle? No, that's not very likely. The liquid is going to flow to the outside of this, to the extremes of this filter. So depending on what h is, r is affected by what h is. R is not a free agent here. And if we want to see how they are linked, we look at this situation. It's a little confusing to look here. Let's just draw a cross-section of the cone. We had, this is 5 inches, and this is 20 inches. Now, let's say there's this much liquid in here. This is R, and this is H. What we're looking at is two similar triangles. We have, let's just look at the right side here. We have the smaller right triangle, and we have the bigger right triangle. And now these triangles are similar, they have the right angles, they share this angle. This is in both the smaller right triangle and the larger right triangle, and of course they share the third angles as well. These triangles are similar, and we have a rule that says that corresponding sides of similar triangles are in proportion. So R is to H as 5 is to 20. R is to H. In other words, for the smaller right triangle, the horizontal leg is to the vertical leg, as in the larger right triangle, the horizontal leg is to the vertical leg here. R is to H as 5 is to 20, or multiplying both sides of this equation by H. We multiply the left side by H and the right side by H. The H's cancel here. We get R is equal to 5 over 20, or 1/4 H. 5 goes into 24 times. So multiplying both sides by H, we get R is equal to 1/4 H. Multiplied both sides by H. So R is always 1/4 H if it's going to be in this filter. And it's not possible for H to be 20 and R should be 1 inch. We now see the actual mechanism here is that the radius is always going to be 1/4 of the height. Okay, so let's put that into the given as well. R has to be 1/4 H. Now that's what we're looking for, because by substituting this value for R into this equation, we'll be able to get an equation just linking V and H. And since we know dV dt and we want to find dH dt, we will have the perfect setup. So V is 1/3 pi R squared H, or 1/3 pi R squared H, but R is equal to 1/4 H, or H over 4. 1/4 H, or H over 4. So V is 1/3 pi. Now H over 4 squared would be H squared over 16 times H. So V is 1/3 pi h over 4 squared would be h squared over 4 squared, h squared over 16 times h. Or v is, let's see, pi over 3 times 16, pi over 48, h cubed. So here we have just what we wanted, an equation linking v and h. And since we know dv dt and we want to find dh dt, if we differentiate both sides of this equation with respect to t, we'll be able to complete the problem. So let's do that. Let's take derivatives of both sides of this equation with respect to t. The derivative of v with respect to v would be 1, but with respect to t it would be 1 dv dt. And the derivative of pi over 48 h cubed with respect to h would be pi over 48, the constant, times the power, 3, h to the 1 less power. With respect to t, it would be this times dh dt. Or dv dt is, okay, 3 goes into 48 16 times, so pi over 16 h squared dh dt. So dv dt is pi over 16 h squared dh dt. If you're having trouble with this particular maneuver here, remember that if v had been, for example, 5h cubed, I think most of you would have no trouble. You would have said dv dt is 5 times 3 h squared dh dt. Because you'd say the constant times the power, h to the 1 less power. So 5 times 3, you'd have 15h squared dh dt. If you can do that, then you can do this. The only difference, instead of having a coefficient of 5, we have one of pi over 48. But it's the same idea. Just like we had the 5 times the 3h squared dh dt, we have the pi over 48 times the 3h squared dh dt. So don't let the pi over 48 throw you. Now, we know dv dt, and we know h at the moment in question. We're looking for dh dt. Okay, so dividing both sides by pi over 16h squared, dh dt is equal to dv dt over pi over 16h squared. dv dt is pi over 16h squared dh dt, so dh dt is dv dt divided by pi over 16h squared. Now we could invert and multiply by 16 over pi h squared. We're a little cramped for space here, so let's just finish the problem up like this. dv dt in this problem is minus 4 cubic inches per second. Minus 4 cubic inches per second over pi over 16. Now, h squared, at the moment in question, h is 12 inches. Okay? So let's see what we have. We have a minus sign. We have cubic inches per second divided by square inches. So we expect to end up with inches per second, which would be suitable because we'd want a height unit over a time unit. That makes sense. Let's see, we have in the numerator 4, and in the denominator we have pi over 16 times 12 squared, which is 144. Now 16 goes into 144 9 times. So our final answer is minus 4 over 9 pi inches per second. minus 4 over 9 pi inches per second. Notice that we would expect the h dt to come out negative because h is a decreasing quantity. H is the level of the liquid in the filter. And maybe it started up here at 20 and it's decreasing as the liquid runs through the filter. So just as V was decreasing and dV dt was negative, H is decreasing. So we're not surprised that the h dt is negative. So dH dt is minus 4 over 9 pi inches per second, or to answer the question, how fast is the depth of the liquid decreasing when the level of the liquid is 12 inches deep? You could write, for an answer, the level of the liquid is decreasing at the rate of 4 over 9 pi inches per second, or approximately 4 over 9 pi is approximately 0.14 inches per second. Okay, so either write that the h dt is minus 4 over 9 pi inches per second, or sometimes students will say, but I did the problem, the back of the book did not have the minus, because they've rewritten it into English, and instead of saying the h dt is minus 4 over 9 pi inches per second, they say the level of the liquid is decreasing at the rate of 4 over 9 pi inches per second. If it was changing, it's changing at the rate of minus 4 over 9 pi inches per second. Once we say the decreasing, we don't need the minus. So if the problem said, how is the level of liquid changing? It's changing at the rate of minus 4 over 9 pi inches per second, which means it is decreasing at the rate of 4 over 9 pi inches per second. In our next example, we have a 13-foot ladder leaning against a wall. The bottom of the ladder is pulled along the ground away from the wall at the constant rate of 2 feet per second. How fast will the top of the ladder be moving down the wall when it is 5 feet above the ground? Okay, let's draw a picture to illustrate what's happening in this problem. We have a 13-foot ladder that's leaning against the wall. And this is our right angle. We have two variables. We have the distance of the bottom of the ladder from the base of the wall here. Let's call that x. And we have the height of the ladder on the wall, how high it reaches up on the wall. Let's call that y. Now let's understand what's happening here. We have, the ladder's length is not changing, but x and y are changing. We have the bottom of the ladder being pulled along the ground away from the wall at the constant rate of 2 feet per second. So you have somebody pulling the ladder out here at the rate of 2 feet per second. Okay, imagine, if you will, you have some guy up here, he's painting, and some clown comes and pulls the ladder out from the bottom. This guy starts to fall. He'd like to calculate the rate at which he's falling to the ground. Okay, there's nothing better to do, so that's what he wants to do. Now, to understand how these variables x and y are changing, imagine, if you will, that originally the ladder, 13 feet long, was like this. This was y, and this was x. But the guy is pulling it out here. Now what's happening is the ladder hasn't changed, but now y has decreased and x has increased. We have still a right triangle. And eventually what's going to happen is, of course, the man is going to fall to the ground, and the ladder is going to be flat on the ground. But right now, You see what's happening? Y is decreasing as we pull the ladder out, and x is increasing. So we have a situation, the 13 feet, the length of the ladder does not change, but x and y are changing. Let's go back to our original picture here. Let's see what we're given and what we're hoping to find. Okay, we're told that somebody is pulling out the ladder, the bottom of the ladder, okay, at the rate of 2 feet per second. Since x measures this distance, that means the x dt is plus 2 feet per second. X is increasing at the rate of 2 feet per second. Remember, as we pull on this base of this ladder, x goes from a smaller quantity to a larger quantity. It's increasing. We're looking to find how fast will the top of the ladder be moving down the wall. Y represents the distance between the top of the ladder and the ground. So we want to find the rate of change of y with respect to t. We want to find dy dt at the moment when, when the top of the ladder is 5 feet above the ground, at the moment when y is 5 feet. We have dx dt, we want to find dy dt. The ideal situation is an equation linking x and y. And we have that because we have a right triangle. And the Pythagorean Theorem tells us that x squared plus y squared must be equal to 13 squared. So we're given an equation linking x and y. The sum of the squares of the legs of this right triangle is equal to the square of the hypotenuse. X squared plus y squared equals 13 squared. We know dx dt is 2 feet per second. We want to find dy dt. Now, we will not be surprised to find out that dy dt at the end will turn out to be negative, because just like as x is increasing as time passes, y, this height, is decreasing. So we would expect to find that dy dt ultimately will be negative. Okay, let's take our original equation, x squared plus y squared equals 13 squared, and differentiate both sides of this equation with respect to t. The derivative of x squared with respect to x would be 2x, but with respect to t, it's 2x dx dt. The derivative of y squared with respect to y would be 2y, but with respect to t, it's 2y dy dt. And the derivative of 13 squared of any constant is going to be 0. So 2x dx dt plus 2y dy dt is 0. We'd like to find dy dt, so let's solve this equation for dy dt. 2y dy dt is equal to negative 2x dx dt. I subtracted the 2x dx dt from both sides of the equation. So it's over there now with a minus sign. And we want to solve for dy dt, so I'm going to divide both sides of this equation by 2y. And the 2's cancel. And we have that dy dt is minus x dx dt over y. We divided both sides by 2y, so on the left we have just dy dt equals, the 2's cancel, minus x dx dt over y. And now we're ready to substitute into this equation. So dy dt is going to be minus x dx dt over y. We were told that dx dt is plus 2 feet per second. Now, we're doing this at the moment when y is 5 feet. However, we have to figure out what x is. Okay, we have our ladder. ladder is always 13 feet long, but x and y, of course, are changing. At the moment when y is 5 feet, this is not being drawn to scale, we want to figure out what x is. Well, since we have a right triangle, x squared plus 5 squared must be equal to 13 squared, or x squared plus 25 must be equal to 169, or x squared must be 144, or x would be plus or minus. We reject the negative. For this physical problem, x is equal to 12. So at that moment, x is going to be 12 feet. Okay, so we can substitute in the value of 12 feet here. So at the point in question, the ladder was 13 feet. That doesn't change. When y is 5 feet, x is 12 feet. If you happen to know that this is a 5, 12, 13 right triangle, you could have saved this calculations. We have a 3, 4, 5 right triangle, 5, 12, 13. And there are other Pythagorean triplets that you may remember, and that saves a little bit of calculations. Anyway, back over here, we have minus x, which is 12 feet. The x dt is 2 feet per second, over y, which is 5 feet. The final answer is minus, which is what we expected. The feet cancel. The final answer is in feet per second. And we have 12 times 2, 24 over 5, minus 24 fifths, or if you multiply by top and bottom by 2, 48 tenths, so minus 4.8 feet per second. Now, the minus because y is decreasing. If you want to answer the question was, how fast will the top of the ladder be moving down the wall? The top of the ladder is moving down the wall at the rate of 4.8 feet per second. It's moving down the wall at the rate of 4.8 feet per second. The minus tells you that y is decreasing and that the ladder is moving down the wall. Okay, in this problem, example 4, a boy flies a kite at a height of 60 feet above the level of his hand. If the kite flies horizontally away from the boy at the rate of 5 feet per second, at what rate is the string being let out when the length of the string released is 100 feet? And we assume that the string that's being let out is always remaining taut. In other words, the wind is pulling the kite and we have the string is tight, and it's forming a situation that looks something like this. We have our boy here, and this is the level of his hand. He's flying the kite, and he wants to fly it at a height of 60 feet above the level of his hand. Now the wind is pulling the kite horizontally away from the boy at the rate of 5 feet per second. So the kite is moving in this direction at the rate of 5 feet per second. And we have two variables here. We have x, the distance between the boy and an imaginary point directly underneath the kite, and y, the amount of string that's being let out. This is the string connecting the boy to the kite. And as I said, this string is taut. Okay? Now, see what we're given and what we want to find. We're given that the kite is flying horizontally away from the boy at the rate of 5 feet per second. So if the kite is moving in this direction horizontally at 5 feet per second, then this imaginary point underneath the kite is also moving at the rate of 5 feet per second. And since x is the distance between that point and the boy, we assume that dx dt is plus 5 feet per second. The kite is moving at 5 feet per second in that direction, and so is this point here, which is the vertex of this right triangle. Vertex of this right angle here, in this right triangle. So this is also moving at the rate of 5 feet per second. So we have dx dt, And we want to find the rate at which he's letting out the string. Well, the length of string here is y. We want to find the rate of change of the string with respect to time, or d string dt or dy dt. At the moment when there are 100 feet of string has been released, at the moment when y is equal to 100 feet. So we have dx dt, 5 feet per second. We want to find dy dt, and of course the best way to do this is if we had an equation linking x and y. And once again we have a Pythagorean relationship here. The Pythagorean theorem holds in this right triangle, and we know that x squared plus 60 squared is equal to y squared. And the last problem was the hypotenuse that was remaining fixed. Here, the boy wants to fly this kite at this height of 60 feet. Okay, so this is staying fixed. And he's going to be letting out more string, as is necessary in order to keep this situation. Okay, so we have x squared plus 60 squared is y squared. We know dx dt. We want to find dy dt. So we'll take our equation, x squared plus 60 squared is y squared, and we're going to differentiate both sides of this equation with respect to t. So, derivative of x squared with respect to t is 2x dx dt. The derivative of 60 squared with respect to t is 0 because it's constant. Derivative of y squared with respect to t is 2y dy dt. And we know dx dt, we want to solve for dy dt. So let's divide both sides by 2y. And we'll have that dy dt is equal to 2x dx dt over 2y, dividing top and bottom by 2, x dx dt over y. And now we're ready to substitute into this equation. dy dt is x dx dt over y. Let's see what we know. We're interested in the particular moment when y is 100 feet. And we're told that the x dt is 5 feet per second. We need to know what is x at that moment. Let's draw a picture of what's happening at that particular moment. At that particular moment, here is the kite. Now we know the kite is 60 feet above the level of his hand. In general, x and y are changing. But when y is 100 feet, what is x? Well, if you use the Pythagorean theorem, x squared plus 60 squared is equal to 100 squared. X squared plus 3600 is equal to 10,000. Or x squared, subtracting 3600 from both sides, is equal to 6400. X would be plus or minus, but we'll only accept the positive answer, the square root of 6400, which is 80. So x is going to be 80 feet at that moment. Of course, if you know about 3, 4, 5 right triangles, this is a 3, 4, 5 right triangle times 20. Okay, 3 times 20, 60. This is 20 times 3, this is 20 times 5, and this is 20 times 4, or 80 feet. Finishing up the problem, dy dt is positive, which makes sense. As x increases, the kite is flying in this direction. X is increasing, y is also increasing. We're letting out the string. So we do expect a positive answer. The feet cancel. Feet per second is the final answer, the unit of the final answer, which makes sense. We would want a y unit over time unit, over a unit of y over a unit of t, so feet per second. And we have 80 times 5, which is 400, over 100, 400 over 100, or 4 feet per second. So the string is being let out at the rate of 4 feet per second. Okay? Since more string, okay, the string is increasing, so we expect dy dt to be plus. It's positive, and we're letting out the string at the rate of 4 feet per second. And that brings us to the end of this problem and to the end of this videotape.